And we now move on, basically straight from where you left, with Tom Nichols giving an overview on the actual neuroimaging meta-analysis methods.
Thanks, Simon. Okay, so I'll be trying to give an overview with respect to the statistics and sort of both give some context to the neuroimaging meta-analysis methods, in particular by referencing what's done in traditional meta-analysis, and then go through the different techniques that are used, the two most commonly used methods, and then sort of some thoughts on what do we still need to work on, where can the methods be improved. Okay, so if you look in a sort of this is actually from a review paper for doing traditional meta-analyses, it lists all these things that you should do in a meta-analysis of, say, clinical trials. And so we can see sort of how we go, and actually it's a really excellent overview by Felix, and captured most of these things. So you have to define what you're interested in, you have to specify what are the studies that you're going to consider, and that's sort of facilitated by the brain map database. You have to identify all the eligible studies. And again, that's within the scope of the brain map database. That's really easy. Now, of course, the studies are all collected for you. But now, normally, when you validate the data vigorously, this goes. It usually consists of going through each of the papers and making sure that you've recorded the means and standard errors correctly. So now, in the brain map database, you basically are you're sort of trusting that data is correct. But there are still some things you could do. Maybe make sure that all the points are in the brain. Make sure there's aren't sort of funny things there. But that's maybe you don't have as rich tools developed as a non-imaging meta-analysis. This is very fiddly. Are the batteries low in this? Right. So the other thing you do with a traditional clinical trial meta-analysis is you make a plot of each study's effect, and you compare that, and you also crucially represent the uncertainty, usually with like a triangle or some bar. Now that's one thing that we can't really do in neuroimaging meta-analysis, because all the results from each study are just a collection of points. We can visualize them, but we don't have a good way of measuring the uncertainty or visualizing the uncertainty associated with each one. And then in the other thing that we kind of halfway have, so compute an average effect, and that's what ALE is doing. Basically, it's giving us a map of the average effect. But then also, current practice in traditional meta-analysis is to emphasize the use of random effects, and I'll spell out what that is exactly, but we don't really, I'm not quite sure we have that in neuroimaging meta-analyses. And then lastly, you do various sensitivity analyses, look for publication bias, and basically sort of change various things. You can do some of this in meta-analysis. You can sort of change your criterion for what studies you included and excluded, but these same tools are not really, there's not as rich a set of tools for neuroimaging meta-analysis as there is for traditional meta-analysis. All right, so I'll just quickly review this. I won't say too much because actually this year for the first time we have a whole separate talk on image-based meta-analyses. But in the non-imaging world for, say, clinical trial, here are the types of meta-analyses that you have. Is there a laser? Yeah, great. So what you can do is do meta-analyses based just on the p-values or the z-values converted into p-values. They're known by Fishers or Stauffer's. But again, if you look at the literature, these are regarded as kind of deprecated methods. They're not really supposed to be used because they're not working in real data units. And so also differing n can induce a heterogeneity and sort of making these less than comparable, making these measures less than comparable. So it's recommended that you work with the actual data units in something called a fixed effects meta-analysis, where you have the estimates and their uncertainties and you combine them. And this allows you to weight different studies. So the more precise studies get more weight and the less precise studies get less weight. Now, the only problem with these is that this neglects inter-study variation. So if there is a sort of systematic, well, if there's sort of random variation in the population studies or the exact methods between different studies, then that could sort of falsely lead you to believe there's an effect when there isn't. So the sort of current best practice is to use a random effects. So this is explicitly modeling the between-study variation, admitting that different studies do things differently. They've sampled somehow different populations, and we like to incorporate that into that. So it still is giving each study a weighted effect, but the weights are based on the standard errors get reported in each study and the inter-study variation. And then lastly, also, something that's kind of a default and you might not even see mentioned nowadays in traditional clinical trials meta-analysis is that there's always regressors included. So anything that you know about the different studies that might explain on interesting variation, you include, and you include them in a regression, and they call that meta-regression. And again, you can do that with fixed or random effects. Okay, so that's what a person working in a hospital doing clinical trials meta-analysis would know about meta-analysis. Now let's go back to imaging. Okay, so what's the simplest thing you could do? Well, the simplest thing would be if you actually had univariate measures from, say, an ROI. And then we actually could use all those methods in the two slides I just showed you. But this, of course, would require the percent bold and their standard error. And it's basically impossible to do because, well, we're brain mappers. We generally don't use ROIs. We're not like in PET where you might find a good literature of papers on the caudate response. We generally produce maps. And so unless you actually have ROI-based reports, and again, this is not searching voxels inside an ROI. This is an average of an ROI. Unless you have those from different authors, you can't do this. And of course, you may say, well, why not? Why, in some papers they report the peak percent bold inside an ROI. And again, that doesn't help us because that's affected by this bias. So basically, if you imagine, for example, that there's a region that had an activation of a true bold effect shown here in orange, well, of course, the true bold effect is going to be perturbed by some noise. And how are you going to measure this effect? Well, you're going to measure it by the peak location. And so that peak location is, you're not going to measure the randomly down below the true signal area. You're going to measure the randomly above the true signal area because you're using the max. So this is the problem. This is why it's so difficult to extract data from existing published papers in terms of the response magnitude. So yeah, basically we can't do that. I think I've learned the trick now. I just wave it. Okay, so what could we do if we had the image data? So this is the second type of meta-analysis. And again, I won't say too much because we have a separate talk given by Camille that is by me later. Well, if we had the T images, we could use Fisher-Stauffer's methods. If we had the contrast images, we could do an on-weighted random effects method. And if we had both the contrast and errors, images and their variances, we could do a sort of the best practice one. So the best practice is a random effects model that incorporates both the within subject coming from the Varkopes and the between subject variance, which FSL's flame feet does estimate. However, this is all well and good, except nobody shares their data, so you actually can't do this in practice, except in small-scale cases where you maybe have all the data in your lab, or you've done the laborious work of actually contacting authors and getting it. So I won't say more about this. I'll talk more about that after the break. Okay, so I'm going to talk about two coordinate-based meta-analysis methods that are based on the XYZ locations. That's the activation likelihood estimation method and the multi-level kernel density analysis method. And just to say, there's also a third one here that is also has some nice software, but it's basically similar to these two, and that's assigned difference mapping. So both of these methods, ALE and MKDA, are kernel-based methods. They basically are trying to recreate the thing we do not have. We ideally would like the contrast map or the statistic map everywhere in the brain. We don't. We just have the XYZ points. How can we reproduce that? Well, we use a kernel method. We are going to replace each point with some function. So in one of these methods, like MKDA, uses a spherical kernel, just a solid equal intensity, whereas ALE is using a Gaussian kernel to replace these points. And then as a result, you get an estimate, not a very true one, but an estimate of the image-wise estimate. And when we combine these, each one of these we call a meta map, an individual study map, and we combine those into a meta-analysis map. But from there, it actually starts to look like a traditional neuroimaging analysis because, well, you now have a statistic map kind of looks kind of different, and it was created in very different ways from what we're used to, but we still have the question of trying to find what areas are real, where are the true positives. So we have to figure out some way of thresholding this image, and we might do that while controlling the family-wise error rate or the false discovery rate on clusters or voxels. So it's just as we normally do. How do you actually get the p-values? Well, you cannot use standard parametric results or random field theory. You have to use something called a Monte Carlo test to figure out what are the typical values of this strange statistic image. And the actual way you do that is you, and I was mentioning this before, under the null hypothesis of no structure. So our null hypothesis is that there's no particular arrangement of these points. And so this Monte Carlo test proceeds by taking each study and just shuffling randomly in space, or just randomly plopping down a number of foci equal to the number that was seen in the study, and then reanalyzing the data. Okay, so let's walk through the ALE MKDA. I'm sorry, ALE, modified ALE version. So if we start with, sort of, say, 3 studies with these points here, the maps we get for each, we start by plopping down a kernel at each of these locations, and then we take each one of these and we make a study map over here. So it's like a convolution, but it's not quite a convolution. It is an arithmetic based on probability. But I'll explain that in a second. So we get one of these maps for each study, and then we combine these into an ALE map. And the interpretation for a single foci is that this is the probability of observing a foci at that location, given that we saw one foci there. And this is how, it's not exactly a convolution, it's actually this probability combining function. So this function that we see here is the sum of the probabilities back here minus their intersection, assuming that these are independent events. And so this is the interpretation that we get, that for a given spread, this is the probability of observing one or more foci at a given location. That's what this arithmetic is supposed to be doing. So one of the problems that people were aware of really early on is that you can have some studies that just happen to report a lot of foci. They will create a sort of a large intensity height in their study map. And the concern was that study could dominate, even though that maybe isn't there. That study just happened to report lots of foci within a given area, not that it actually had lots of information there. It was just sort of an arbitrary choice by the author. So Simon and colleagues revised the method to make a modified ALE method that, first of all, came up with a very clever way to avoid the Monte Carlo test. So you can just do this sort of directly. You can work out what this null distribution is. And also, very interestingly, they figured out that this kernel size tends to vary systematically with n. And they worked out an empirical function that maps the sample size of your study to how broad this kernel size. So it's still a particular choice, one particular choice, but at least it's a little less arbitrary. It's actually based on some empirical data that they collected. So the voxelwise test is now very fast, though if you want to do the clusterwise test, you still have to do the Monte Carlo method. Okay, so MKDA is actually quite similar, except there's just one change, which is instead of plopping down Gaussians, we plop down boxcars in one dimension, which is spheres in 3 dimensions. And the way that the KDA specified that you combine these is you just sum them up, and then you just average these to make the MDA study map. But this has the same problem that you can see, that these can pile up if there's some studies that report too many. So a modified, the multi-level kernel density analysis basically addresses this problem, but actually in a very simple way. It simply truncates. It does this computation and then just never lets that get higher. Now that may seem sort of an arbitrary sort of a modification of the method, but it does have an interpretation, whereas this map up here is the number of foci that were within distance r. This one is an indicator, 0, 1, was there a foci within distance r? So it's also an interpretable map, and it addresses the problem of this overpiling up. Okay, and then we average these together, and then we get a final map which has an interpretation of This is the weighted. This is an average of how many studies. So this final MKDA map has the interpretation. What was the average number of studies that had one or more foci at this location? And also, they usually will do a weighted average, so they try to account for the space, just like in the previous method. And an ALE, modified ALE, uses the sample size to adjust the kernel bandwidth f. Here, they use the sample size to do a weighted average when they do this combining here. And also, there's the modified KDA, the updated MKDA also uses a different way of doing the resampling. Instead of just randomly sampling all the points, they randomly shuffle the clusters of points. So these 3 points would not be, under resampling, would not be shuffled randomly around the brain. They would be moved as a set of 3 points randomly around the brain to reflect the clustering that's present. Okay, so what are some of the limitations of these coordinate-based approaches is that what I mentioned is what is an effect size? What does an effect size mean in this imaging setting? Because again, they make a big deal of it in traditional meta-analysis. What is your effect size? What is its uncertainty? In MKDA, well, we have this sort of proportion of studies that result that show one or more foci in the given radius R. And in ALE, this is the probability at an individual voxel that one or more foci occurred for the given Gaussian probability model. So we don't have any standard errors for this. And there's also this issue of sensitivity, which is basically when you see an effect, does it mean, is it like a random effects inference or is it more like a fixed effects inference? Is there a minimum number of studies that you need to satisfy a result? And is that what's driving the activation, or is it the proportion? So if it turns out that 5 out of 10 studies give you an activation, you might think that's great. But if 5 out of 100 studies, well, is that great? It's very sensitive. Maybe it's a very sensitive method, or maybe that's a bad thing. Maybe that's just reflecting that this is more of a fixed effects versus random effects. But Simon and I are going to talk more about that this week. So just as a reference for what am I talking about in intensity-based meta-analysis, what is the random effects? Well, usually what we think about is this. So we think that if I'm talking about the bold response magnitude, I know that in each subject there's fairly small measurement error because we have 500, 1,000 times scans. We have time series of length of 1,000 on each subject. And so that gives us rather small intra-subject variability. But that's not what's important. What's important is the between-subject variability. And this is what we mean when we do a random effects analysis in traditional brain mapping, is that we're accounting for this variability, not just this variability here. So what exactly does it mean in the spatial context of coordinate-based meta-analysis? I think it's a challenging thing. And so if we change, I'm going to reuse my figure and just actually call this a transect of space now instead of percent bold magnitude. Are we talking about just this sort of the spread of these points in space? And again, we have the same question about how much does it take to get significance. Because in contrast, when we do inference in ALE, what we're doing is we're doing an assumption that under the null hypothesis, this is completely homogeneous. So it's weird. The easiest thing to get our head wrapped around in the spatial context is the spatial spread. But it's not. It's something quite different from the way we usually think about random effects inference when it's talking about intensity. So I think it's very hard. I basically think we need to come up with a new definition of what does it mean for random effects in point data, because the previous notion doesn't directly apply. I need to do something about these clickers. This is okay. So let me just skip this for the sake of time. That was just some self-promotion. So here's an idea. Here's to point out that when a traditional traditional meta-analysis does a sensitivity analysis, these are some of the things that they're looking for, and in some cases we might be able to do these in brain imaging. Certainly, if we have the z-scores for a subset of the values. And that is if you plot z-scores versus the square root of the sample size. Well, as the studies get smaller and smaller and smaller, the effect should diminish. If you're looking at a true effect, it should get smaller and smaller as you have fewer subjects. Because again, this is not the true effect, this is a z-score. This is not x bar, this is a z-score. So with more and more subjects, this should go do. And so that's one thing you can look for. You can actually do a regression and see if this falls down and intersects 0. Because if this doesn't intersect 0, that suggests there's some sort of bias. And it turns out you can do a similar thing with just the number of foci that occur, in fact, and do a logistic regression for whether studies show one or more foci in a given region or not. And if so, if you see a relationship like this is what you'd expect, that as the sample size goes to 0, the prevalence of these studies should fall down and get close to 0, whereas if there's a sort of horizontal line where it doesn't intersect 0, that'd be reporting bias, or maybe it's indicating, in this setting, a null result. So basically, these methods have been done in one-off, but we don't have the tools to sort of do this sort of on a routine basis. And here's another way you can look at this. So these are beginning to look like the plots that you see in a traditional non-imaging meta-analysis. And what I've shown here is simply the proportion of studies that show one or more foci in the right amygdala. And but I did this just to illustrate that it's hard to know, without knowing what the reporting standard of each study, it's hard to know whether these are significant results. So what this is saying is that overall, over these 154 studies, without breaking them up over all the groups, we can be confident that the proportion of studies reporting something is around 30%, and that's the confidence intervals. Now you might say, well, that's not too much. Is that different from 0? Well, it turns out if every study was using a whole brain family-wise error-corrected threshold, this is how many. That's the fraction that we'd expect. We basically expect no results in any study if there's no results, if the null hypothesis was true. However, if the null hypothesis is true, and then you consider these more and more sort of generous methods of thresholding. So, for example, we just do the small volume correction on the right amygdala, or what if just half of all the studies were using an uncorrected threshold on this region, or what if all the studies were using uncorrected? What proportion of studies would you expect to see one or more to show one or more foci? Well, in fact, actually these go up. So suddenly. So here, if we're just using a small volume FWE threshold, this is still significant. But certainly, if even just half of all the studies are using uncorrected thresholds, then at least in these two groups, for example, happy and sad, are actually showing responses that are consistent with chance in this setup. So this is just one way we can try to look at and try to do a sensitivity analysis. But again, we don't sort of have automated methods on this. And also, I just in a bit of self-promotion, I'm doing work with a student where we're trying to estimate the prevalence of missing file drawer studies. And you can find that on Wednesday, poster 4038. All right. So the conclusions are is that ideally we'd be able to use a intensity data. We don't have that. And when with coordinate-based meta-analysis, we have two tools that I've just described, and there are more out there. But I think there's still opportunities to improve this and provide all of the tools that non-imaging meta-analysis has at its disposal. Thank you.
Oh, thank you, Tom, a lot for the great talk.